This screencast is going to go over the basics from first year chemistry on acids and bases, and it'll just serve as a refresher to get us ready for our acid-base equilibrium and continuing our study of equilibrium. So there's different definitions for acids and bases, and it kind of depends on which particular compound you're looking at and which definition makes sense. So we have the Arrhenius definition of what an acid and base are, as well as the Bronsted-Lowry. Now there's also the Lewis acid-base theory, which we'll actually just talk briefly about at the very end of this chapter, but they have removed that from the AP curriculum. So an Arrhenius acid is any substance that increases the H plus in solution. So a substance that increases the concentration of H plus in solution. And then a base is any substance that increases the OH minus in a solution. So that goes with Arrhenius. I would say that Bronsted-Lowry is probably the most common acid-base theory we use, and we typically talk about just the transfer of protons. So acids are proton donors. That means they give up their protons. And bases are proton donors, are proton acceptors. Okay, so with Bronsted-Lowry, we have the conjugate acid-base theory that we'll talk about in just a sec. These have gotten shifted over a little bit, but HA is any generic acid. So the acids begin with H unless they're organic acids, and then they end with that carboxylic or carboxyl off at the end. So if we talk about a generic acid being placed in water, the acid will shed its H plus and give it to water, and then what will be left of water is the H3O plus, the protonated form of water, and then the A minus. So this is our acid. Water in this case is acting as a base because it is accepting the proton. A minus is going to be our conjugate base, and then the H3O plus is our conjugate acid. So we typically pair up the ones that look most alike, and then those are your acid-base pairs. Conjugates are always going to be on the product side. Your acids and bases are always going to be on the reactant side. Now the difference here is we have this left-right arrow, right? So if we were going to move from right to left, A minus, in order to become HA, would have to gain a proton. So that's why A minus is considered a conjugate base, because if it were to gain, it would be acting as a base. So the kind of simplified reaction is completely fine to write. Just remember that even though we're not writing water, it is still there. And we really don't ever just have protons floating around. Those are protons that are attached to a water molecule, making the H3O plus. But either of those are acceptable. So if you think back to equilibrium and our K expressions, we're now going to add, so in our last unit we had Kc and Kp, we're now going to add on a Ka. So Ka is our product concentrations raised to their exponents over our reactant concentrations. Okay? So that's just a basic Ka expression. So for hydrochloric acid, we're going to put them in water. And we're going to have a single arrow on hydrochloric acid. This is not an equilibrium because this is a strong acid, right? So it's going to make Cl minus, the H plus goes to the water and makes H3O plus. If we wanted to do the simple, we could just say HCl forms H plus Cl minus. For the ammonium ion, NH4 plus in water, okay, this is a weak, so it'll give up its H and form H3O plus, and then NH3 will be left. For the simplified version, if you think, well, where would the proton go, you can just draw it as H plus and NH3. Okay, so if we want to find conjugate acid-base pairs, it's definitely easier to do it on the full. So this is our acid, this is our conjugate base, this is our base, and H3O plus is our conjugate acid. And then for NH4 plus, going to NH3. This is our acid. NH3 is our conjugate base. Water here is acting as a base, and its partner is the conjugate acid. Now we won't have a part C for this one because hydrochloric is a strong, right? But for our NH4+, Ka would be equal to, on top, I'm just going to do the simplified version. So H plus times the concentration of NH3 all over the concentration of NH4+. So that would be your products over reactants like we've been doing. Alright, so acid strength. In first year chemistry, we spent most of our time talking about strong acids and strong bases. We learned the list of strong acids. If you haven't, I feel like they're listed in here somewhere. You do need to learn those because then you're not having to learn 100 different weak acids. If you know the strong, it's not on the list, then you know it's going to be weak. So just some terminology as a review: monoprotic, meaning it has 1 proton; diprotic, meaning it has 2. You could also call that a polyprotic. So polyprotic, like a phosphoric acid and H3PO4. You could just call it polyprotic. Oxyacids are going to be the ones that have oxygen atoms attached, and so typically those are coming from your 8s and your ites. And then organic acids, we studied those. We have the C double bonded OOH. It's just that H that comes off of those. So water is amphoteric. So we saw that word in first year chemistry. It isn't the only amphoteric substance, but it can gain a proton or it can lose a proton. So we actually get an equilibrium from this. And you've seen this last year, you just had no idea what in the world a K was. So Kw is a constant. So if we take the concentration of H plus times OH minus over water, right, and the water won't appear in the equilibrium expression, we get this constant. So that's called the autoionization of water. So water basically donating a proton, and then the other water sitting there accepting the proton, right? So this constant is true at 25 degrees Celsius. That's where this comes from, pH plus POH equals 14. If you remember, we used that last year, not really knowing where it came from. You just kind of took my word on it. All right, so in general, this should be review. If the H plus concentration is greater than the OH minus, then we're going to be an acidic solution, right? Because if you think of your pH scale, you've got acid, neutral is 7, and then base. So if H plus is bigger, then that means we're on the acidic side of the scale. If OH is bigger, that means we're basic. We're on this side of the scale. And then if they're exactly equal, then that solution is neutral. And depending on temperature, right, it may not be 7. So that's kind of a new twist to pH that we're going to see. All right, so here we're going to do some basic review calculations. If you remember, if you put a little p in front of anything, that just means the negative log of. So if I'm given the OH minus concentration, right, and I want to know the H plus concentration, I would just need to use this Kw. So Kw is OH minus times H plus, and that's equal to a constant as long as we're at 25 degrees Celsius. So if I know the OH minus is 1.0 times 10 to the negative 5th, then I can solve for the H plus because their product is equal to that. And this is actually one you can do without a calculator. And so when I divide the 1 and the 1, I obviously get 1. And then I have 10 to the negative 14th divided by 10 to the negative 5th. So I would get 10 to the negative 9th molar. So the OH minus is greater than the H plus, so that means the solution would be basic. And if you remember how we found pH, you would actually just negative log that and get a POH of 5, which would be a pH of 9, which is basic. All right, so for H plus, same KW, so we're going to do that down here. So 1.0 times 10 to the negative 14th equals 1.0 times 10 to the negative 3rd times the OH minus now. So again, we can do that without a calculator, hopefully. And OH minus is tiny, 1.0 times 10 to the negative 11th molar. So in this case, our H plus is greater than OH minus. So this would be acidic. And if we were to negative log that, we would get a pH of 3, which matches what we know about acid pH. So here's our pH scale. Like I said, the P out in front just means negative log of whatever follows, so negative log of H+. POH is the negative log of OH-. If you wanted to work in reverse, you do the anti-log, or 10 to the negative pH, 10 to the negative POH. And then this is true if you're at 25 degrees Celsius. You can certainly still use that. Okay. Now, one note on logarithms and significant figures. This is not something I want you to worry about, but I do want you to know there is a different rule, and so if it feels like sig figs are off, they're probably actually not. So the number of decimal places in the log is equal to the number of significant figures in the original number. Okay. So that means if this pH has 2 decimal places, then that means the original concentration, the thing that you were taking the log of, had 2 significant figures. So the sig figs here need to match the decimal places, which I know will be a little weird. All right. So for finding POH, I think the easiest would probably be just to do 14 minus 6.88, and you get 7.12. To just assume that that 14 has an infinite number of sig figs when you subtract, and so it'll just be limited by that. So then to get our H+, we would do 10 to the minus 6.88. So that has 2 decimal places. So the concentration would be 1.3 times 10 to the negative 7th molar. And then our OH-, you have 2 choices. You could certainly use kW here, or you could just say 10 to the minus 7.12. and then solve for that concentration with 2 sig figs, 7.6 times 10 to the negative 8 molar. They're asking you to classify as acidic, basic, or neutral. So our pH is what we always want to classify on, because that's the scale you've seen since, I don't know, probably 5th grade. So if the pH is less than 7, that means this thing would be acidic. I would never classify based on that, or you can certainly look at the concentrations. This is negative 7 exponent, that's negative 8. So H+ is bigger, so that's why it would be acidic. All right, so try, go ahead and pause the screencast and try those, and then you can check your work in just a sec. All right, here are your answers for solutions B and C, so just check to see how those went and how your classifications went. So the last thing we want to talk about is our 7 strong acids. So you do need to learn your list of 7 strong acids. H2SO4 is strong in terms of only that first hydrogen. So if I were to write the dissociation reaction, it would have a one-directional arrow for the first, what we call deprotonation. That just means losing your proton. And then for the second one, we would have equilibrium arrows, because this one is an equilibrium. So this would have a Ka value. It's Ka1, and don't worry about why it's Ka1. Is way, way bigger than 1. This would have some number that you could look up in a table. So we assume 100% dissociation, okay? So the nice thing about that is that means that if HCl fully dissociates, if this was 0.10 molar, then that means both of those are 0.10 molar. So if we wanted to find the pH, we would just negative log the 0.10. And so we would get a pH of 1.00. So we've got 2 significant figures in our concentration, so our log is going to have 2 decimal places. All right, for HNO3, this is considered an exceptionally dilute solution. I'm not really seeing these on the AP exam. Textbooks like to include them. So think about what this means. The concentration of the nitric acid, right, is going to be 10 to the negative 11th, which is so small, the autoionization of water actually takes over. And so this, right, those are both equal to 1 times 10 to the negative 7th molar. So this reaction is actually more important than having this tiny little concentration of HNO3 in solution. So for the exceptionally dilute case, this is the equilibrium that takes over. And you would just say your pH is equal to 7, because this is dominating, not that. So typically, if your concentration is less than negative 7, this will take over and you ignore the acid.